We will continue with our discussion on pulse modulation schemes that we started last time. You may recollect that we talked about pulse amplitude modulation, right, and just to quickly recap, pulse amplitude modulation is essentially a manifestation of sampling process. You are basically sampling the flat top, sampling the message signal, and the amplitudes at those discrete times instance at the sampling instance are transmitted in terms of amplitudes of either impulses, which is not practical, more practically in terms of finite width pulses. Basically the kind of sampling process that you go through is a flat top sampling process. The value of the signal that you pick up could be any value in the pulse duration, but the example that we took up, the development that we carried out was based on the leading edge modulation scheme. That is, the amplitude of the pulse was proportional to the amplitude of the signal at the leading edge of the pulse, right. That is why the when we pass this impulse sample signal to generate the flat top sample signal through a filter, the filter impulse response that we took was a pulse function with a width of tau starting from 0 to tau, right. And we found how to demodulate this signal. If the demodulation had two aspects, one was the equalization process, which equalized for the fact that flat top sampling involves some spectral distortion, right, in the baseband region. To compensate for that spectral distortion, we first equalize the spectrum and then pass it through an ideal low pass filter to reconstruct our continuous time signal back. Just the sampling theorem revisited for you, and that is also pulse amplitude modulation. I went through it rather quickly because I was sure that all of you already know this stuff, and I just have to recap it for you. In case you have forgotten some of it, please do review it. More importantly, we will now turn to the two other kinds of pulse modulation schemes that are commonly used, namely pulse width modulation and pulse position modulation. Let us look at pulse width modulation first. So, as the name obviously implies, the parameter which you modulate here is the width of the pulse. That is, you want to make the instantaneous pulse width at each pulse duration proportional to the amplitude of the message signal. So, that much is obvious. Obviously the first question is, how can we do such a thing? How can we implement this pulse width modulation? So, to do that, let us just go through a series of pictures which will illustrate one way by which you can generate a pulse width modulated signal. So, let us say you have a message signal like that, right. To start with, you generate a PAM signal, pulse amplitude modulation signal, which is very easy to generate because all you need to design is a sampler. I have not given you any circuits for designing a sampler, but that is very easy to do. All you to build a sampler, what do you need? All you need is a switch which will allow the signal to either pass through or not to pass through. During the on period of the pulse, it will allow it to pass through, right, and of course you will have to clip it if you want to have a flat top sampling signal, and when the switch is off, it is not allowed to pass through. So, essentially it is a switch. So, you first generate a pulse amplitude modulated signal in the same way as we discussed earlier, right. That is the first step. So, you generate this is the message signal MT, and this is a PAM signal corresponding to this message signal, right. Now, to this signal we simultaneously, let me call this x1t, we simultaneously generate another set of pulses of constant amplitude, but whose shape is triangular in nature. And synchronized with these pulses. So, this is what they look like. set of triangular pulses with this shape are generated. Again, they are very easy to generate. There are methods of generating sawtooth pulses, and that is what you do. So, as a function of time, this is what the two waveforms look like. Let us call it P of t, right, and then I add up these two waveforms.
So, what is the amplitude of PT?
Some constant amplitude, it is not important, right, suitably selected so as to satisfy practical requirements, it is not very important. Now, you simply add up these two signals. So, what will you see? You let me redraw that Pm signal. So, on top of this pulse, you will get this triangular pulse, right. You added up these two, right. On top of this pulse, you will get a similar triangular pulse, but this will now go up to a slightly lower height, because of the fact that the Pm pulse to which you are adding it has a lower amplitude, right. Similarly, here it will go up like that. This will be the sum of the two. Okay. So, you are likely to generate a waveform like that when you add up these two. Having done that, all you need to do is slice this waveform at some point, right, have a threshold, and if this only the signal, so pass this through a comparator. Let us say you have heard of a comparator. A comparator is a device, basically an open loop operational amplifier will serve as a comparator, as an excellent comparator. One of those inputs is this signal, which is x1t plus p of t, right. So, that is one of the inputs, x1t plus p of t, and the other input is a reference voltage which is equal to this constant voltage, let us say V, right. So, the output will be 1, the output of the comparator will be a positive output for when the input signal is above the threshold value, above the voltage V, and will be either 0 or negative depending on how you design the circuit. Let us say it is 0 when the input voltage is less than that, right. So, what will this produce? This comparator output will generate pulses of constant amplitude, right, because it only give either a positive pulse or a 0 pulse, either the output will be positive or 0. So, during this interval you will get a pulse width like that, right. At this point you get a pulse width of this kind. Now, this will be an even narrower pulse, right, and so on and so forth. As you can see, the width of the pulse that you will generate will be proportional to the amplitude of the pulse on which it is riding, on this on which the triangular pulse is riding, and that is precisely what you want, right. So, this becomes your PWM waveform. Are you with me? In fact, it is obvious because of the fact that this is a triangular pulse. The point of intersection of this constant voltage line with this added waveform would generate different durations during which the pulse amplitude, the sum amplitude is larger than the pulse width. Here it is larger than the value V for a much larger time than here, and so on and so forth, right. So, you will get a large pulse width here, a smaller one here, and a still smaller one here. The pulse width will increase here again and increase further here, because during this time this voltage is greater than the reference voltage. So, you will get a pulse of constant amplitude, but whose duration will depend on the duration for which this remains above this threshold voltage. So, that is really as simple as that. So, this is one way of generating the PWM waveform. There are others, but this is one way.
So now my information about MT is now in the width.
In the width of the pulse, right. So, that is what you will transmit. Now,
The amplitude of this pulse will not be constant, depends on the
amplitude will be constant because the comparator output just produces a fixed amplitude output of some value, simply depending on whether this voltage is more than this or less than this. That is what a comparator will do, because comparator has to tell you whether this one is larger or this one is larger, right, and this it does by generating a voltage value which is either positive, some fixed value, or 0, something or 0. So, basically the output will be a binary waveform here, the comparator output will be a binary waveform, right, which is what we have drawn here, right. Its operation is, suppose you have call this V1 and you call this V2, the output voltage V0 is some fixed value, let us say k volts for let me write it like this, V0 is k for V1, let us say greater than V2, it is equal to 0 for V1 less than V2. That is what it does, and that is what you have got here. That is what a comparator will do. Okay. What about demodulation? To look at how do you get the original message waveform back. So, as you can see, this is a different kind of sampling. You are still doing sampling, but the sample information, the amplitude of the waveform is not directly embedded in the amplitude of the pulse. It is embedded in the width of the pulse. Now, to look at the demodulation, what was the demodulation based on for the case of PWM? It was based on the spectrum of the PWM signal. Remember that? The spectrum of the PWM signal, if you recollect, or the impulse sample signal, is essentially a replicated spectrum. If this is your baseband spectrum, then it gets replicated at the sampling rate, around the sampling frequency around 2fs and so on and so forth. It is a periodic spectrum, and the demodulation was based on the fact that the spectrum of interest for the continuous signal lies in the central lobe around the baseband. So, all you have to do is remove the periodic components, remove the components above the bandwidth of the signal, right, by passing it through an ideal low pass filter, and you have your continuous signal back, continuous time signal back. So, to do the demodulation for PWM signal, therefore, ideally we should look at the spectrum of the PWM signal, right. Yes, please.
We have this V0 equal to 0 when V1 is less than V2, then are we losing information?
No, our objective is to generate, to embed the amplitude information of these pulses into width information of constant amplitude pulses. That is our limited objective.
So in the
That
case
we are able to
you
do.
get 0, you don't get a pulse there.
Sorry.
The case when the x1 t plus pt is less than v.
Yeah. So, obviously you have to design the values of this triangular pulses and these amplitudes of these pulses have to be designed in such a manner that this operates properly, right. That is a matter of detailed design. Surely we do not want to have a situation where the sum of these two is below the threshold value V. So, the value of the threshold voltage will be decided by the range of the sum pulses, right. You have to choose them carefully so that you always get a pulse of some width corresponding to the amplitude of interest, right. So, that is a matter of design which I am not getting into, I am sure it is easily done, right. So, coming back to demodulation, if you want to do a similar thing now, you have to understand what is the spectrum of the PWM signal. Unfortunately, the spectrum calculation of the PWM signal is very involved, right, and it is beyond the scope as well as the time available to us to do it, right. I will just give you a reference for those of you who are interested in going through the calculation, and it is like, you know, the spectrum calculation of an FM signal or PM signal is much more involved than the spectrum calculation of the AM signal, right. It is a similar kind of complication, in fact a little more involved in that. And there is a very famous book in the area of communication. It is a classical book, it is a communications classic for all time, and that's a book by Schwartz, Bennett and Stein. It's a book from McGraw-Hill, and I think it is a 1966 book. It's a very old book, but still regarded as a communications classic book, right? It's called Communication Systems or something like that. So those of you who are interested in a detailed spectrum analysis of the PWM waveform can go to this book and look at the derivation. But let me just recap the result for you. It's a little complicated, but it gives some insight, and that insight is important. Therefore I'm just quoting the result from this book. I'm not deriving this result here. We simply don't have the time, or in fact it's outside the scope of this discussion. The PWM signal, let's call it x of t. If I call this PWM waveform as x of t, can be expressed in terms of a series expansion like this. There is a constant value half of h. Basically you are doing some kind of a Fourier series representation of this. Actually it is not a periodic signal. One can see that it is not a periodic signal in general, right? But still it is possible to come up with some kind of a harmonic like representation. It's not exactly a harmonic representation, as you will soon see, and which looks like this: half h minus half h, and there is a parameter beta which I will define shortly, cosine 2 pi fmt. Here I am assuming that your modulating signal mt is a pure tone signal. So mt is cosine 2 pi fmt. So that appears in this expansion, plus 1 by pi sigma m equal to 1 to infinity. There is a large number of terms here. The mth coefficient is minus 1 to the power m minus, and very surprisingly or not so surprisingly, the Bessel functions appear again. Just like when we went from am to fm, Bessel functions appear. J0 of m pi beta into 1 by m sine 2 pi fm 2 pi m f sub st. M fs is the fs is the sampling rate of the pulses, right? Sine 2 pi m f sub st, right? That is one term. And then there is another very complicated huge term, but let me write it just for the sake of completeness. So it may appear to be waste of time, but it is instructive. So therefore I will just write it. There is a double summation now. M pi beta once again. I hope you can read it. Sine of 2 pi m f sub s plus n f sub m into t plus n pi by 2 plus sine of 2 pi m f sub s minus n sub f m f sub m t plus n pi by 2. Is it complicated enough for you? Yes. Good. Let's see some pattern in this madness, if there is anything. H here refers to the amplitude of the PWM pulses. Right? And beta is a kind of modulation index, which I will not define formally, but basically it's like this: beta would be equal to 1 if the maximum possible pulse width, if you use the maximum possible pulse width that you can have. Suppose what is the rate of these pulses? What is the interval between pulses? It's 1 by fs. So what is the maximum possible pulse width you can have? 1 by 2 fs, isn't it? This is 1 by fs. So what is the maximum possible pulse width you can have without causing interference with the next pulse? It's half of this pulse width, pulse interval, right? So 1 by 2 fs. So when you choose a maximum pulse width to be equal to 1 by 2 fs, beta is said to be 1, right? So that's like 100% modulation, right? That's what basically. So beta is this parameter. If you choose the maximum pulse width to be less than 1 by 2 fs, beta is suitably scaled down appropriately, right? So that is what beta is. It's a modulation index, measure of modulation index. Now let's see whether there is any method in this madness. What you will notice is that this signal has a DC component, has the desired message empty as one of the additive terms, and then has components corresponding to the sampling frequency of the pulses, as well as sum and difference of these frequencies, MFS plus NFM and MFS minus NFM, right? With for all possible values of M and N. And of course the amplitude of these components will somehow depend on the Bessel function values, right? If you want to plot this, the spectrum therefore will look something like this. We are plotting it as a function of frequency. So as you can see, there is a DC component. Let me use a different color. There is a DC component, this one, and then there is a component at FM, right? Then you have a component at Fs, and then you have components around Fs, sum and difference. Now it turns out that how many components you have around Fs, n equal to 1, will depend on various factors like beta and h, etc., particularly beta, the modulation index, right? So when beta is very, very small, that is you are using only a fraction of the maximum possible width that you can have, right? When beta is very small, then around Fs also you have only two components, namely Fs plus Fm. It's like narrowband Fm. It becomes like narrowband Fm. So Fs plus Fm and Fs minus Fm, and then you have components around 2 Fs, and these amplitudes will be different, and so on. But then there can be additional terms here, right? So just like we have many components in an FM signal, just rather only the two side bands, we have many components here around Fs, 2 Fs, 3 Fs, and so on and so forth, not just plus Fm and minus Fm, right? However, the interesting fact is, and the useful fact is, that as far as the baseband part is concerned, it contains only a DC component and the desired signal component, right? So what kind of spectrum you have around Fs and 2Fs is not very important, as long as my baseband signal is intact. So to recover the baseband signal, what should I do? Again, just put a low pass filter, because all these signals will simply disappear once again. All these components will still. So the demodulation for a PWM signal is therefore once again the same low pass filter that you are using for the case of PAM or a sample signal. They can, of course, this is true when beta is small. So when beta is, let's say, typically much less than 1, this spectrum is, for example, typically between 1.1 to 0.2, right? The way I have plotted it. As beta increases, you can have larger number of components around Fs, right? And that will imply that the guard band that you have for your problems like aliasing to occur will become smaller, right? So you have to watch out for that. But for small values of beta, the baseband spectrum more or less remains intact, and all you have to do is recover the signal that you want, the baseband signal that you want, by passing it through a low pass filter. So PWM waveform is coming in, pass it through a low pass filter, and that will recover your message signal plus a DC component which you can remove. Alright. Any questions?
So the DC component is independent of message.
Yeah, half of edge.
Independent of message.
Yes.
So why you are passing it? What is the need of it?
How I am passing?
What the need of it?
No, how do all I am saying is let it come. Eventually, I can always remove a DC component by putting put a coupling capacitor or something at the output, right? So let the DC component come. It will come if you have a low pass filter. The DC component will pass through that, right? So let it come. It doesn't matter. It doesn't do any harm to us. That's all I'm saying.
Sir?
I don't know whether you got your question. Yes, please.
Sir, in pulse modulated waves, sir, whole of the frequency axis is filled with the message bandwidth. So sir, how this helps in transmitting, because only one signal will block whole of the frequency axis.
Now that's a good
Where
question. Unfortunately, I don't have time to go into the details of the answer to this question, but roughly it is like this. Typically, you use pulse modulation schemes where you are not worried too much about bandwidth as such, right? Also, secondly, it's of course one can always come back and say that there is hardly any system in which you are not worried about bandwidth, right? The second part of the answer is that I have drawn all these pictures using rectangular pulses, right? In practice, we very rarely will use rectangular pulses, right? Rectangular pulses will have this problem of bandwidth, right? Of course, your concern is slightly different. Your concern is that you have this repeated spectrum because of the sampling itself.
It blocks all of the whole
Right.
frequency.
So,
Time division multiplexing.
the very fact that you agree to use pulses implies that you have sufficient bandwidth to transmit the spectrum, right? Because that is implicit in time division multiplexing. So you can't do much about that. So basically, we are saying that okay, our data rate of interest is typically much smaller. Our information rate is much smaller than the bandwidth available to us. It's only that it's convenient to work with time division multiplexing in this case rather than frequency division multiplexing. So bandwidth becomes a secondary issue in this particular situation right now, right? Really speaking, the bandwidth is not secondary because ultimately you must remember that in a certain bandwidth you have to transmit a given number of messages. That will still happen. It will turn out that the bandwidth efficiency of time division multiplexing and frequency division multiplexing will be of the same order. It will not be very different. But that's a matter of detail. Unfortunately, we don't have too much time to go into it. So maybe some self-reading will be required for you to take care of that. But that's a good question. Let's now come to pulse position modulation. So what is pulse position modulation? As the name implies, now you will not have variable width pulses, you will not have variable amplitude pulses, you will have pulses whose positions from some fixed reference position is proportional to the message signal. So that is how you define pulse position modulation. Pulse displacement from some specified reference point, specified time reference is proportional to the sample value of empty, right? Of course, if you want this to be true, typically either you will have to have positions on both sides of the reference if you want positive and negative values of empty. Our best thing is to keep empty always positive by adding some positive bias to it, right? So that you always go on one side of the reference, right? That's a matter of detail. How do you generate this pulse such signals? Can you suggest something? Any suggestion for generating Ppm waveform? Anyone? Suppose I have let me give you a hint. suppose I have a PWM waveform. Can I convert this into a PPM waveform? Just like I converted a Pwm waveform into a PWM waveform, is there a simple method of converting a PWM waveform to a PPM waveform?
Sir, switching, sir, producing an impulse.
Yeah, so let's look at that. Let's say this is your PWM waveform. I am just drawing some waveform arbitrarily. How can I convert this into a so this is PWM, right? This time interval is 1 by Fs, which is fixed. Now you want to generate a pulse. Remember, this width is proportional to the amplitude of the message. So basically, where you want to produce your pulse? At this point, right? Here you want to produce it at this point. Here the reference point is this. So the reference points, time reference points are these, right? What you want to do is generate pulses whose position here is this, and the pulse width is constant and the pulse amplitude is constant, whose position here with reference to this position is this, and so on and so forth. This is the kind of waveform you are looking for, right? This is your PPM waveform. So any idea how we can generate that? Is it clear? This is what we want. Yes.
But you have information about where my pulse is starting also, because I'm having suppose
Yeah, this is true. This is the information about pulse starting. So,
differentiating.
all right. If you differentiate, you will get two pulses, a positive edge and a negative edge. What do you do with that? Remove the positive edge, and then you have a negative edge, and that has to be converted into a positive pulse of this kind somehow. There is a very simple way of doing it by using a device called a monostable multivibrator. I discussed that in some other context, maybe. No, I discussed as stable up. You done that in your digital circuits? Yes or no? You know about bistable? You know about flip flops?
yes, sir.
Okay, those are bistable multivibrators. They have two stable states, right? They have two stable states. As you trigger it, it goes from one stable state to another stable state. A monostable multivibrator is like a flip flop, except that it has only one stable state. So when you trigger it, it goes into an unstable state, and after some time it comes back to the stable state, right? That is what a monostable circuit is. I will not go into the circuit here, because we do not have, it is not a circuit digital circuits class, but that is what a monostable multivibrator does. So you have a trigger here, and the trigger will make it go into the unstable state. It will stay in that state for some time, right, and will come back to the stable state. So let us say the unstable state corresponds to a 1 output, and the stable state corresponds to a 0 output. So temporarily produce a 1 output. After some fixed time, it will come back to, which is what you want. You want temporarily to go to this 1 output, and after some time you want to come back to the stable state, which is a 0 output, and so stay there till the next trigger comes. And where should the trigger come? It should come at the trailing edge of the PWM pulses, right? So basically, you need a monostable multivibrator which triggers at, so this triggers at trailing edges. You can always design monostables which trigger at the leading edge, or monostables which trigger at the trailing edge. Okay.
So, but in PPM, once I have a pulse having some bandwidth, some width, when I am having no information from that pulse which I am having except for the position of it, you can either have an impulse at that point.
Impulses are very difficult to handle. They will have very large bandwidth. That is why you always go for finite width pulses. The moment you have finite width pulses, you are actually reducing the bandwidth requirement, right? Isn't it? Impulses of infinite bandwidth. Right? So you always have finite width pulses. The larger the width you can have, the better it is, but the width will be decided by how many signals you want to multiplex in time, right. Suppose within this duration you want to transmit many more signals, right. So then obviously there is a limit even to the pulse width you can have for individual signal. Suppose, see, this 1/2 fs maximum width I talked about was when you are transmitting only one signal. Suppose you are transmitting 10 signals, then the maximum pulse width you can have is 1/20 fs, because this second signal will also take its range of pulse widths, right. So it depends on the pulse width that you will end up using will be finally dictated by the number of signals you want to multiplex in time. Okay. So that is a ppm signal. That's how you can generate a ppm signal. So the demodulation, once again one has to go into the spectrum. I think you won't like me to write another expression of that kind, right. But without writing the complete expression, I will just write the first two terms of the expression, which are useful to understand. To understand what the nature of the demodulator would be. Actually, ppm and PWM bear the same relationship to each other that FM and PM bear to each other, right. But if you think about it, you can convince yourself about this issue, and you will find that there is a similar relationship here. So if you look at the ppm signal in detail, and I am only looking at the first two terms of that expansion, please do not disturb like that. X of t is equal to fs minus beta f sub m sin 2 pi f sub m t plus all those horrible looking expressions which are not right, which basically contains terms like mfs plus nfs, right, which are and your message signal was a cosine 2 pi f m t. So what do you see? And this is a message signal. This term is not cosine 2 pi f m t, but its derivative actually, as you can see, right. So in a way, when you do ppm, in fact, if you remember, somebody said that you can differentiate a PWM signal and come close to a ppm signal. So you can see that from the spectrum expansion also, right. And therefore that also gives you a clue to how to demodulate. Now can you give a clue?
Integrate and pass through a low pass.
No, for demodulating you first pass it through a low pass filter and then integrate. So you have a ppm demodulator, and the output of the ppm demodulator is integrated to give you the ppm demodulator output will give you sin 2 pi f m t. Or low pass filter essentially will give you a sin 2 pi f m t, isn't it? If you low pass filter it, you will get this term. To get cosine 2 pi f m t, you integrate it back, right. You integrate this, fm sin 2 pi f m t will become cos 2 pi f m t. So demodulation of a ppm signal is really fairly straightforward. Pass it through a low pass filter, that is your ppm demodulator. There is another way of doing it. You can convert ppm signal first to PWM signal if you wish, and then pass it through a low pass filter. I will leave that as an exercise for you to work out yourself, how to convert a ppm signal to a PWM signal. Okay. So that is a second possibility, ppm to PWM to low pass filter. That is the second possibility. So this is one method, this is the second method. Think about this method on your own. So that is a very brief introduction to pulse modulation schemes. These analog pulse modulation schemes that I just mentioned, we have covered them very briefly. As I said, they are largely used in telemetry applications, largely, or they were till very recently. That was the picture. Of late, they have become important also in other kinds of applications. For example, these pulse modulation schemes have become very important in optical communications. I will just like to mention some of these things for your benefit. Right. In optical communications, where you try to modulate the intensity of light in proportion to the message signal, right. Sometimes you like to transmit in the pulse mode, and when you transmit in the pulse mode, it is convenient. It's useful to consider all these options, right. Width of the pulse, amplitude of the pulse, that is intensity of the pulse, and position of the pulse. That is one. Another application where it has become recently very important is some, I do not know whether some of you have heard of these wireless communications, which are called ultra wideband wireless communications. Right, where you are not transmitting over very long distances. Maybe you are designing a LAN in a limited area, or actually it is presently more used in defense applications of some kind. Basically, you do not have a carrier once again, you are transmitting baseband pulses in air, very narrow baseband pulses here, which is very difficult to do because the antennas have to be very, the corresponding antennas become very difficult to design, efficient antennas. But nevertheless, they are very secure for various reasons, because the average spectrum floor is very low, because pulse widths are very small, right. They are ultra wideband, and therefore the signal level is so low that somebody who wants to intercept it cannot see it. That is one advantage of that. The average spectrum floor is very low. So these have become very important of late, and a lot of research is currently happening in this area. And when you do this, basically you have, since you are transmitting baseband pulses, information in them can be embedded either through amplitude modulation, Pm, or pulse width modulation, or pulse position modulation, right. So just I thought some of the modern flavor about these pulse modulation schemes I should just briefly mention before we close this topic. But remember, what we have discussed is analog modulations. We discussed analog modulation of sinusoidal carriers earlier, and we discussed analog modulation of pulse carriers here, right. Why analog? Because the message amplitude is embedded in some parameter of the carrier, which is again analog in nature, with its width or height or position, right. Now, as against that, as against analog modulations, we can do this embedding also digitally. So, you can also have digital pulse modulations. Now, what is meant by digital about it? Basically, what we mean by that is that the final pulse waveform that you transmit on the channel is essentially binary in nature, right. It is only a 1-0 information that you transmit, and somehow information about the message has to be encoded into this 1-0 form, right. That is about all. And in fact, that is what eventually leads to digital communications, which of course you will learn in much more detail in a subsequent course, but I will just try to give you a flavor of what happens in digital communications at the end of this course, right. So, basically you are representing your information in which is present in a message signal, which is basically analog in nature, via some digital representation, right. That is, by digital I mean something which has a fixed number of levels, rather than analog means you can have any amplitude in a continuous range from -infinity to +infinity. When you talk about digital, you are saying that no, we will not have any possible value, you will have values which are discrete in nature. Basically, digital means discrete amplitude first. So, when I refer to the word digital, it refers to discrete amplitude. The simplest example of discrete amplitudes is to have only two amplitudes, ones and zeros, but a more general representation would have several amplitudes, maybe 4, maybe 8, maybe 16, right. You can have a fixed number of amplitudes. You work only with a fixed number of amplitudes. Now, how do you represent a signal which has continuously varying amplitude with another signal which has only a discrete set of amplitudes to work with, right. And that, when you do that, you are able to convert that analog information into digital information, right. Why should we do this? I think let us first discuss that. Why? The how of it is something that perhaps some of you already know. Perhaps you have learnt about analog to digital converters, right. So, the how of it is something that may not be that new to you, right. Although there are two methods that I want to discuss here, the one which corresponds roughly to your A to D conversion. The second is much simpler, it is called delta modulation, and I will discuss both of these very briefly. But more importantly today, I want to discuss the why of it. What benefits are possibly accruable when you go from representing information of interest which you want to transmit from analog to digital. Can you try to answer this question? More accuracy. Okay, let me write down some of the answers that you are. More accuracy, less noise, easy processing. Anything else? Okay. If you were to vote for the most important reason for these three, which one would you vote for? As communication engineers, you should have guessed the answer. It has to do with noise, right? Because noise is our bane in some sense. We have to worry about noise all the time, and it is this feature which is very important. So, basically remember what, when you went from AM to FM, what did we buy? We traded bandwidth with performance in the presence of noise. So, noise is of constant concern to us, and that is the major advantage you are worried about. Accuracy, yes and no, depends on how you look at it. Easy processing also yes and no, depends on how you look at it, but yes, less noise is the crucial thing. Now, how can that come about? Because noise in the channel will be the same no matter whether you transmit binary pulses over it or whether you transmit analog messages over it. How can it possibly come down? Can you think about that?
But digital world can be easily recovered because it will be other.
Now, let us see. Let us see. Here is a digital pulse, right? And you have said this noise. Where is it digital now? At the receiver, what will happen? By itself, it does not do anything.
In one sense, if we have some analog signal and somehow by some small noise, its amplitude gets very large. That variation will not be very much seen in this vehicle case.
Okay. The key to the answer is, this is correct, and Rajat is nearly there, but I am not sure whether I fully understand him. The important point is the following: you don't let noise do the real harm to you, and you recover the information much before that, right? So, noise is getting more and more as you are traveling, as your signal is traveling, right? Signal is becoming weaker, and the noise that is getting ready is becoming larger and larger. That is what will happen when you actually transmit the signal over any communication medium, right? There are some clean media and some not so clean media, but invariably this is the behavior, whether it is cables, wires, or wireless or any other medium. This is what will eventually happen. Signal will become weaker and weaker as it travels, as it propagates, and noise will become stronger and stronger, right? When you come to this situation, you are already in a hopeless situation. You may not be able to do very much, right? So, what you can do is make sure that before it becomes too weak and before the noise overrides the signal too much, recover the signal and make it absolutely a clean signal once again. You regenerate the signal, regenerate the clean signal, right, through a simple device which is called a repeater, right, a digital repeater. Repeater normally in conventional sense only meant amplifier. The signal becomes weak, you amplify it, make it stronger and retransmit it, but an amplifier will not do, because an amplifier will amplify both signal as well as noise. So, a repeater here would have to be of a special kind. It will have to be a what is called a regenerative repeater, right? In the sense that you have to clean up the pulse and transmit a fresh, absolutely clean pulse once again. So, as the signal is propagated, it becomes a little noisy on the way. So, the pulse spins like that, and you clean up this pulse and convert this into a pulse like that by a very simple clipping and match filtering and clipping kind of operations, and then retransmit it, and keep doing this regeneration as and when required. And if you are able to do that, you will eventually get a reason, right? And that is how you are able to reduce noise in digital communication, right? And that's the essence of trading of bandwidth with noise once again, because bandwidth will increase because you are transmitting pulses rather than continuous time signals. However, you cannot do this. It's clear that you cannot do this with analog transmission, right? You can't carry out such a cleaning operation for an analog message, because there is no way to separate the two. There is no way to convert that into something else.
So, but cleaning the signal so many times may danger this message signal itself.
No, converting a pulse back to a pulse, a clean pulse, that's all you are doing. Every single pulse that is coming in, which is somewhat noisy, is being converted to a clean pulse in the same position. So, the information is intact.
You don't have any averaging of signal.
No, some will happen. I mean, this is I am giving an idealized answer. Obviously, you won't get perfect answer, right? But then it will be much better than what you can get through analog transmission. Okay. So, that is a reason why digital communications is so important as compared to analog communication, right? So, I will stop at this point, and we will discuss two methods of converting analog information into digital information in the next two classes. Thank you.